Okay, so let's get started with the actual technical content. So remember from last time, we gave an overview of the class. We talked about different types of models that we're going to explore: reflex models, state-based models, variable-based models, and logic models, which we'll see throughout the course. But underlying all of this is machine learning, because machine learning is what allows you to take data and tune the parameters of the model so you don't have to work as hard designing the model. So in this lecture, I'm going to start with the simplest of the models, of reflex-based models, and show how machine learning can be applied to these type of models. And throughout the class, we're going to talk about different types of models and how learning will help with those as well. So there's going to be 3 parts. We're going to talk about linear predictors, which includes classification and regression, loss minimization, which is basically setting an objective function of how you want to train your machine learning model, and then stochastic gradient descent, which is an algorithm that allows you to actually do the work. So let's start with perhaps the most cliched example of machine learning. So we want to do spam classification. So the input is X, an email message. And you want to know whether an email message is spam or not spam. So we're going to denote the output of the classifier to be Y, which is, in this case, either spam or not spam. And our goal is to produce a predictor, F. Right? So a predictor, in general, is going to be a function that maps some input X to some output Y. In this case, it's going to take an email message and map it to whether the email message is spam or not. Okay, so there's many types of prediction problems. Binary classification is the simplest one, where the output is one of 2 possibilities, either yes or no. And we're going to usually denote this as +1 or -1. Sometimes you also see 1 and 0. There's regression, where you're trying to predict a numerical value, for example, let's say housing price. There's a multi-class classification where Y is not just 2 items, but possibly 100 items, maybe cat, dog, truck, tree, and different kind of image categories. There's ranking, where the output is a permutation of input. This could be useful, for example, if the input is a set of articles or products or web pages, and you want to rank them in some order to show to a user. Structure prediction is where Y, the output is an object that is much more complicated. Perhaps it's a whole sentence or even an image. And it's something that you have to kind of construct. You have to build this thing from scratch. It's not just a labeling. And there's many more types of prediction problems. But underlying all of this, whenever someone says, I'm going to do machine learning, the first question you ask is, OK, what's the data? Because without data, there's no learning. So we're going to call an example XY pair is something that specifies what the output should be when the input is X. Okay? And a training data or a set of examples, the training set, is going to be simply a list or a multi-set of examples. So you can think about this as a partial specification of behavior. So remember, we're trying to design a system that has certain types of behaviors, and we're going to show you examples of what that system should do. If I have some email message that has CS221, then it's not spam, but if it has lots of $signs, then it might be spam. So remember, this is not a full specification of behavior. These 10 examples or even 1,000,000 examples might not tell you what exactly this function is supposed to do. It's just examples of what the function could do on those particular examples. OK, so once you have this data, so we're going to use dtrain to denote the data set. Remember, it's a set of input-output pairs. We're going to push this into a learning algorithm or a learner. And what is the learning algorithm going to produce? It's going to produce a predictor. So predictors are F. And the predictor, remember, is what? It's actually itself a function that takes an input X and maps it to an output Y. Okay, so there's kind of 2 levels here. And you can understand this in terms of the modeling inference learning paradigm. So modeling is about the question of what should the types of predictors F you should consider are. Inference is about how do you compute Y given X. And learning is about how you take data and produce a predictor so that you can do inference. Okay? Any questions about this so far? So this is pretty high level and abstract and generic right now. And this is kind of on purpose because I want to highlight how general machine learning is before going into the specifics of linear predictors. Right? So this is an abstract framework. Okay, so let's dig in a little bit to this an actual problem. So just to simplify the email problem, let's consider the task of predicting whether a string is an email address or not. Okay? So the input is a string, and the output it's a binary classification problem. It's either 1 if it's an email or -1 if it's not. That's what you want. So the first step of doing linear prediction is known as feature extraction. And the question you should ask yourself is, what properties of the input X might be relevant for predicting the output Y? Right? So I say really highlight might be. Right? At this point, you're not trying to encode the actual set of rules that solves the problem. That would involve no learning. That would just be trying to do it directly. But instead, for learning, you're kind of taking more of a backseat, and you're saying, well, here's some hints that could help you. Okay? So formally, a feature extractor takes an input and outputs a set of feature name, feature value pairs. Right? So I'll go through an example here. So if I have abc@gmail.com, what are the properties that might be useful for determining whether a string is an email address or not? Well, you might consider the length of the string. If it's greater than 10, maybe long strings are less likely to be email addresses than shorter ones. And here the feature name is length greater than 10. So that's just kind of the label of that feature. And the value of that feature is 1, representing it's true. So it will be 0 if it's false. Here's another feature, the fraction of alphanumeric characters. Right? So that happens to be 0.85, which is the number. There might be features that test for particular letters. For example, it doesn't contain an @ sign. Or that has a feature value of 1 because there is an @ sign. Ends with .com is 1. Ends with .org is 0 because that's not true. So, and there you could have many, many more features. And we'll talk more about features next time. But the point is that you have a set of properties. You're kind of distilling down this input, which could be a string, it could be an image, or it could be something more complicated, into kind of a ground-up fashion that later we'll see how a machine learning algorithm can take advantage of. Okay, so you have this feature vector, which is a list of feature values and their associated names or labels. Okay, but later we'll see that the names don't matter to the learning algorithm. So actually what you should also think about the feature vector is simply a list of numbers. And just kind of on the side make a note that, oh, this position number 3 corresponds to contains @ and so on. Right, so I've distilled the email address abc@gmail.com into the list of numbers 0 or 1, 0.85, 110. Okay, so that's a feature extraction. It's kind of distilling complex objects into lists of numbers, which we'll see is what the kind of the lingua franca of these machine learning algorithms is. Okay, so I'm going to write some concepts on the board. There's going to be a bunch of concepts I'm going to introduce, and I'll just keep them up on the board for reference. So feature vector is a kind of important notion. It's denoted phi of x, an input. So phi itself, sometimes you think about it, you call it the feature map, which takes an input and returns a vector. And this notation means that it returns, in general, a d-dimensional vector, so a list of d numbers. And the components of this feature vector we can write down as phi1, phi2, all the way to phi d of x. Okay, so this notation is convenient because we're going to start shifting our focus from thinking about the features as properties of input to features as kind of mathematical objects. So in particular, phi of x is a point in a high-dimensional space. So if you had 2 features, that would be a point in 2-dimensional space. But in general, you might have a million features, so that's a feature it's a point in a million dimensional space. So it might be hard to think about that space, but we'll see how we can deal with that later in a bit. Okay, so that's a feature vector. You take an input and return a list of numbers. Okay, and now the second piece is a weight vector. So let me write down weight vector. So a weight vector is going to be noted W. And this is also a list of D numbers. It's a point in a D-dimensional space, but we're going to interpret it differently, as we'll see later. Okay, so the way to think about a weight vector is that for each feature j, so for example, frac of alpha, we're going to have a real number, wj, that represents the contribution of that feature to the prediction. So this contribution is 0.6. So what does this 0.6 mean? So the way to think about this is that you have your weight vector, and you have a feature vector of a particular input, and the score of your prediction is going to be the dot product between the weight vector and the feature vector. Okay, so that's written w dot phi of x, which is written out as basically looking at all the features and multiplying the feature value times the weight of that feature and summing up all those numbers. So for this example, it would be minus 1.2, that's the weight of the first feature, times 1, that's the feature value, plus 0.6 times 0.85, and so on, until you get this number, 4.51, which happens to be the score for this example. Question?
So the feature extraction with phi of x, is that supposed to be like an automated process, or does it require like a manual extraction or specification of features?
Yeah, so the question is the feature extraction manual or automatic? So phi is going to be implemented as a function, like in code, right? You're going to write this function manually, but the function itself is run automatically on examples. Later, we'll see how you can actually learn features as well. So you can slowly start to do less of the manual effort, but we're going to hold off until next time for that. Question?
So we were talking about weight meaning, and I know that in certain types of regressions, like the weights being a percentage change if this variable leads to a percentage change in the outcome. It doesn't mean this here, right? Yeah,
so the question is about interpretation of weights. Sometimes weights can have a more precise meaning. In general, you can try to read the tea leaves, but I don't think there is maybe in general mathematically precise thing you can say about the meaning of individual weights. But intuitively, and the intuition is important, is that you should think about each feature as a little person that's going to make a vote on this prediction, right? So you're voting either plus, yay, or nay. And the weight of a particular feature specifies both the direction of the vote, whether if positive weight means that that little person is voting positive, and negative weight means that it's voting negative, and the magnitude of that weight is how strongly that little person feels about the prediction, right? So contains at is 3 because maybe like at signs generally do occur in email addresses, but the fraction of alphanumeric characters, it's less. So at that level, you can have some intuition, but the precise numbers and why is 0.6 versus 0.5, that's you can't really say much about that. Yeah, another question.
Does a dot product, is this the same dot product for deeper networks? Like if you have like 4 weight vectors afterwards, is it still like just more products?
So right now we're focusing on linear classifiers. So the question is, what happens if you have a neural net with more layers? There's going to be more dot products, but there's also it's not just adding more features. There's going to be other components, which we'll get to in a later lecture. Yeah?
Do all the weights have to add up to a certain number, or how do you normalize it so the weights don't change the score value by
Yeah, so the question is, do the weights have to add up to something? The short answer is no. There's obviously restricted settings where you might want to normalize the weights or something, but we're not going to consider that right now. Later we'll see that the magnitude of the weight does tell you something. Okay, so just to summarize, it's important to note that the wave vector, there's only one wave vector, right? You have to find one set of parameters for everybody. But the feature vector is per example. So for every input, you get a new feature vector. So, and the dot product of those two weighted combination of features is the score. Okay, so now let's try to put the pieces together and define of the actual predictor. Right? So remember we had this box with an f in it, which takes x and returns y. So what is inside that box? And I've hopefully given you some intuition. Let me go to a board and write a few more things. So the score, remember, is w dot phi of x. And this is just going to be a number. And the predictor, so linear predictor, well, actually, let me call this linear. To be more precise, it's a linear classifier, not just a predictor. Classifier is just a predictor that does classification. So a linear classifier denoted f of w. So f is what we're going to use to denote predictors. W just means that this predictor depends on a particular set of weights. And this predictor is going to look at the score and return the sign of that score. So what is a sign? The sign looks at the score and says, is it a positive number? If it's positive, then I'm going to return +1. If it's a negative number, I'm going to return -1. And if it's 0, then I don't care. You can return +1 if you want. It doesn't matter. So what this is doing, remember the score is a real number. So it's either going to be like kind of leaning towards large positive values, or leaning towards large small negative values. And the sign basically says, okay, you got to commit. Which side are you on? Are you on the positive side or are you on the negative side? And just kind of discretizes it. That's what the sign does. Okay? Okay, so let's look at a simple example, because I think a lot of what I've said before is kind of more the formal machinery behind and the math behind how it works. But it's really useful to have some geometric intuition, because then you can draw some pictures. Okay, so let's consider this case. So we have a wave vector, which is 2, 1, 2 minus 1, and a feature vector, which is 2, 0, and another feature vector, which is 0, 2, and 2, 4. Okay, so there's only 2 dimensions, so I can try to draw them on a board. So let's try to do that. Okay, so here is a 2-dimensional plot. And let's draw the wave vector first. Okay, so the wave vector is going to be at 2 minus 1. Okay, so that's this point. And the way to think about the wave vector is not that point, but actually the vector going from the origin to that point, for reasons that will become clear later. Okay, so that's the weight. Okay. And then what about the other points? So we have 2, 0, 0, 2. So 2, 0 is here. 0, 2 is here. And 2, 4 is here, right? Okay, so we have 3 points here. Okay, so how do I think about what this wave vector is doing? So just for reference, remember the classifier is looking at the sign of w dot phi of x. Okay, so let's try to do classification on these 3 points. Okay, so w is let me write it out formally. So 2, 1, and this is 0, 2. So what's the score when I do w dot phi of x here? It's 4, right? Because this is 2, 0, 0, 2, 2, 4. So this is just a dot product. That's 4. And take the sign. What's the sign of 4? 1. Okay, so that means I'm going to label this point as a positive, right? Positive point. Okay, what about 0, 2? Actually, sorry, this is just to be a -1, right? Okay, this is 2 minus 1. Okay, so if I take the dot product between this, I get -2. And then the sign of -2 is -1. Okay, so that's a minus. And what about this one? So what's the dot product there? It's going to be 0. Okay, so so this classifier will classify this point as a positive, this as a negative, and this one I don't know. Okay, so we can fill in more points, but does anyone see kind of maybe a more general pattern? I don't want to have to fill in the entire board with classifications. Yeah.
The orthogonal, everything to the right of it is positive, everything to the left of it is negative.
Yeah, so let's try to draw the orthogonal. Ouch, this needs to go through that line. Okay. Okay, so let's draw the orthogonal. So this is a right angle. Okay. And what that gentleman said is that the points, any point over here, because it has an acute angle with W, is going to be classified as positive. So all of this stuff is positive, 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 positive. And everything over here, because it has an obtuse angle with W, is going to be negative. So everything over here is negative. And then everything on this line is going to be 0. Okay? So I don't know. Okay, and this line is called the decision boundary, which is a concept not just for linear classifiers, but whenever you have any sort of classifier, the decision boundary is the separation between the regions of the space where the classification is positive versus negative. Okay, and in this case, it separates because we have linear classifiers. The decision boundary is straight, and we're just separating the space into two halves. If you were in 3 dimensions, this vector would still be just a vector, but this decision boundary would be a plane. So you can think about it as coming out of the board if you want, but I'm not going to try to draw that. And that's kind of the geometric interpretation of how linear classifiers work here. Question? Yeah.
It seems like your weight could be any magnitude. Like,
yeah.
So we have 1 less degree of freedom.
Yeah.
Decision boundaries for any bulk.
Yeah. So that's a good point. So the observation is that no matter if you scale this weight by 2, it's actually going to still have the same decision boundary. So the magnitude of the weight doesn't matter. It's the direction that matters. So this is true for just making a prediction. When we look at learning, the magnitude of the weight will matter because we're going to consider other more nuanced loss functions. Yeah. OK, so let's move on. Any questions about linear predictors? So far what we've done is we haven't done any learning, right? If you've noticed, we've just simply defined the set of predictors that we're interested in. So we have feature vector, we have wave vectors, multiply them together, get a score, and then you can send them through a sign function, and you get these linear classifiers. Right? There's no specification of data yet. Okay. So now let's actually turn to do some learning. So remember this framework. Learning needs to take some data and return a predictor. And our predictors are specified by a wave vector. So you can equivalently think about the learning algorithm as outputting a wave vector, if you want, for linear classifiers. And let's unpack the learner. So the learning algorithm is going to be based on optimization, which we started reviewing last lecture, which separates what you want to compute from how you want to compute it. So we're going to first define an optimization problem, which specifies what properties we want a classifier to have in terms of the data. And then we're going to figure out how to actually optimize this. And this modularity is actually really, really powerful. And it allows people to go ahead and work on different types of criteria and different types of models separately from the people who actually develop general purpose algorithms. And this has served to kind of the field of machine learning quite well. Okay, so let's start with the optimization problem. So there's an important concept called a loss function. And this is a super general idea that's used in the machine learning and statistics. So a loss function takes a particular example, xy, and a weight vector, and returns a number. And this number represents how unhappy we would be if we use the predictor given by w to make a prediction on x when the correct output is y. Okay, so it's a little bit of a mouthful, but this basically is trying to characterize, if you handed me a classifier and I go onto this example and try to classify it, is it going to get it right or is it going to get it wrong? So high loss is bad. You don't want to lose. And low loss is good. So normally, 0 loss is the best you can kind of hope for. OK, so let's figure out the loss function for binary classification here. So just some notation. The correct label is denoted y. And the predicted label, remember, is the score sent through the sign function. And that's going to give you the particular label. And let's look at this example. So w equals 2 minus 1, phi of x equals 2, 0, and y equals minus 1. Okay? So we already defined the score as, on example, is w dot phi of x, which is how confident we're predicting plus 1. That's the way to interpret this. Okay? So what's the score for this particular example again? It's 4, right? Which means that we're kind of positive that it's a plus 1. Yeah, question.
I was just wondering, is the loss function generally one-dimensional, or the output of the loss function?
Yeah. So the question is whether the output of loss function is usually a single number or not. In most cases, it is. For basically all practical cases, you should think about the loss function as outputting a single number. The inputs can be, crazy high dimensional. Yeah.
What is it not one-dimensional?
There are cases where you might have multiple objectives that you're trying to optimize at once. But in this class, it's always going to be, one-dimensional. Like maybe you care about, both time and space, or accuracy but robustness, or something. Sometimes you have multi-objective optimization, but that's like way beyond the scope of this class. Okay, so we have a score, and now we're going to define margin. So let me. Okay, so let's actually do this. So we're talking about classification. I'm going to sneak regression in a bit. So score is w dot phi of x. This is how confident we are about plus 1. And the margin is the score times y. And this relies on y being plus 1 or minus 1. So this might seem a little bit mysterious, but let's try to decipher that here. So in this example, the score is 4. So what's the margin? You multiply by minus 1, so the margin is minus 4. Right? And the margin's interpretation is how correct we are. Right? So imagine the correct answer is if the score and the margin have the same sign, then you're going to get positive numbers. And then the more confident you are, then the more correct you are. But if y is minus 1 and the score is positive, then the margin is going to be negative, which means that you're going to be confidently wrong, which is bad. Okay, so just to see if we kind of understand what's going on. So when does a binary classifier make a mistake on a given example? So I'm going to ask for a kind of a show of hands. How many people think it's when the margin is less than 0? Okay, I guess we can kind of stop there. I used to do these online quizzes where it wasn't anonymous, but we're not doing that this year. Okay, so yes, the margin is less than 0. When the margin is less than 0, that means y and the score are different signs, which means that you're making a mistake. Okay, so now we have the notion of a margin. Let's define something called the 0-1 loss. And it's called 0-1 because it returns either a 0 or 1. Okay, very creative name. So the loss function is simply, did you make a mistake or not? Okay, so this notation, let's try to decipher a bit. So if f of x here is the prediction when the input is x, and not equal y is saying, did you make a mistake? So that's, think about it as a Boolean. And this 1 bracket is just notation. It's called an indicator function that takes a condition and returns either 1 or 0. So if the condition is true, then it's going to return a 1. And if the condition is false, it returns a 0. Okay? So all this is doing is basically returning a 1 if you made a mistake and 0 if you didn't make a mistake. Okay? And we can write that as follows. We can write that as the margin less or equal to 0. Right? Because on the previous slide, if the margin is less than or equal to 0, then we've made a mistake, and we should incur a loss of 1. And if the margin is greater than 0, then we didn't make a mistake, and we should incur a loss of 0. Okay? All right, so it will be useful to draw these loss functions pictorially like this. Okay, so on the x-axis here, we're going to show the margin. Right? Remember, the margin is how correct you are. And on the y-axis, we're going to show the loss function, which is how much you're going to suffer for it. Okay, so remember, the margin, if the margin is positive, that means you're getting it right, which means that the loss is 0. But if the margin is less than 0, that means you're getting it wrong, and the loss is 1. Okay, so this is a 0-1 loss. That's the visual that you should have in mind when you think about 0-1 loss. Yeah?
Like less than 0, because we have not defined like when margin is 0, whether the classifier is correct or incorrect.
Yeah, so there's this kind of boundary condition of when what happens exactly at 0 that I'm trying to sweep under the rug because it's not terribly important. Here, it's less or equal to 0 to be kind of on the safe side. So if you don't know, you're also going to get it wrong. Otherwise, you could always just return 0, and then you don't want that. Okay, so is it any questions about kind of binary classification so far? So we've set up these linear predictors, and I've defined the 0-1 loss as a way to capture how unhappy we would be if we had a classifier that was operating on a particular data point, xy. So I'm going to go on a little bit of a digression and talk about linear regression. And the reason I'm doing this is that loss minimization is such a powerful and general framework, and it transcends all of these linear classifiers, regressions, and ups. So I want to kind of emphasize the overall story. So I'm going to give you a bunch of different examples, classification and regression side by side, so we can actually see how they compare, and hopefully the common denominator will kind of emerge more clearly from that. Okay, so we talked a little bit about linear regression in the last lecture, right? So linear regression in some sense is simpler than classification, because if you have a linear predictor, and you get the score w dot phi of x, it's already a real number. So in linear regression, you simply return that real number, and you call that your prediction. Okay? Okay, so now let's move towards defining a loss function. So there's going to be a concept that's going to be useful. It's called the residual, which is, again, kind of trying to capture how wrong you are. So here is a particular linear predictor, linear regressor, and it's making predictions all along, for different values of x. And here's a data point of phi of x, y. Okay, so the residual is the difference between the true value y and the predicted value y. Okay, and in particular, it's the amount by which the prediction is overshooting, the target. Okay, so this is a difference, and if you square the difference, you get something called the squared loss. So this is something we mentioned last lecture. Residual can be either negative or positive, but errors, either if you're very positive or very negative, that's bad. And squaring it makes it so that you're going to suffer equally for errors in both directions. Okay, so the squared loss is the residual squared. So let's do a kind of simple example. So here we have our wave vector 2, minus 1. The feature vector is 2, 0. What's the score? It's 4. Y is minus 1. So the residual is 4 minus 1, which is 5. And 5 squared is 25. So the squared loss on this particular example is 25. Okay, so let's plot this. So just like we did it for a zero on loss, so let's see what this loss function looks like. So the horizontal axis here, instead of being the margin, is going to be this quantity for regression called the residual. It's going to be the difference between the prediction and the true target. And I'm going to plot the loss function. And this loss function is just the squared function, right? So if the residual is 0, then the loss is 0. As the residual grows in either direction, then I'm going to pay something for it. And it's a quadratic penalty, which means that it actually grows pretty fast. So if I'm the residual is 10, then I'm paying 100. Okay, so that's the squared loss. There's also another loss I'll throw in here called the absolute deviation loss. And this might actually be the loss that if you didn't know about regression, you might immediately come to. It's basically the absolute difference between the prediction and the actual true target. Turns out the squared loss, there's a kind of a longer discussion about which loss function makes sense. The salient points here are that the absolute deviation loss has this kink here, and so it's not smooth. Sometimes it makes it harder to optimize. But the square loss also has this kind of thing that blows up, which means that it really doesn't like having outliers or really large values, because you're gonna pay a lot for it. But at this level, just think about this as different losses. There's also something called the Huber loss, which kind of combines both of these, is smooth and also grows linearly instead of quadratically. Okay, so we have both classification and regression. We can define margins and residuals. We get either different loss functions out of it, right? And now we want to minimize the loss, okay? So it turns out that for one example, this is really easy, right? So if I told you, okay, how do I minimize the loss here? Well, okay, it's 0, done. So that's not super interesting. And this corresponds to the fact that if you have a classifier and you're just trying to fit one point, it's really not that hard. So that's kind of not the point. The point of machine learning is that you have to fit all of them. Remember, you only get one wave vector. You have all these examples. You have a million examples, and you want to find one wave vector that kind of balances errors across all of them. And in general, you might not be able to achieve loss of 0, right? So tough luck. Life is hard. So you have to make trade-offs. Which examples are you going to kind of sacrifice for the good of other examples? And this is actually a lot of where issues around fairness of machine learning actually come in, because in cases where you can't actually make a prediction that's equally good for everyone, how do you actually responsibly make these trade-offs? But that's a broader topic. Let's just focus on trade-offs defined by the simple sum over all the loss examples. So let's just say we want to minimize the average loss over all the examples. Okay, so once we have these loss functions, if you average over the training set, you get something which we're going to call the train loss, and that's a function of W, right? So loss is on a particular example, train loss is on the entire data set. Okay, so any questions about this so far? Okay, so there is this discussion about which regression loss to use, which I'm going to skip. You can feel free to read it in the notes if you're interested. The punchline is that if you want things that look like the mean square loss, if you want things that look like the median, use the absolute deviation loss. But I'll skip that for now. Yeah.